Can everybody see the slides?
Yeah, and the transition looks good.
Oh, nice. Zoom becomes working becomes well recently, right? Okay. I guess we can still wait for 2 minutes to have more people to join in. Oh, by the way, so if you haven't started doing homework please start right now, right? We have allocated pretty enough time doing that, given that workload is much lighter. Yeah, all you need to do is just implement support back machines and look at what is the behavior, right? By tuning different hyperparameters and also use stochastic subgradient and also uh, calling some existing libraries to solve SUM in a dual space and investigate their properties. So do not hesitate. The running of the algorithm won't take much time. It will be very fast, but you need to read the documentation and know how to correctly call those like quadratic convex optimization problem, right? And our homework has pointed out all enough documentation. So please start to investigate early, rather than like just 3 hours left and then asking how can I call this library. So this is actually your homework, okay? So I guess we should start. So today we're gonna talk about artificial neural nets. This is I think the most important topic toward the end of this semester. Um, um, and also perhaps neural networks or artificial neural nets are the most popular field, the most known field in machine learning or in artificial intelligence, right? So right now we hear a lot of buzzwords like deep learning, like our intelligence, behaviors, all kinds of stuffs. People like by default thinking about deep neural nets, right? Although the whole area of machine learning is much wider than deep neural nets. Deep neural nets is just one choice, right? So, but it's really important, and you see that I threw our discussion, a few lectures discussion, although it's quite short, right? But you will know all the key ideas behind that, all the key techniques on that. So those key techniques was developed or was invented about 3 decades ago. So all the key techniques for deep learning was invented many years ago, 3 decades ago. But right now, because of the improvement of the computational power, improvement of the computational platform like TensorFlow, like PyTorch, and also the growth of data allow us to say that deep neural nets are really powerful. That's why deep neural nets are kind of like become dominant again. Right? But from the academic point of view, there's really not any like fundamental progress in this area, honestly speaking, right? But right now, people by feeding more and more data into that, we found oh wow, deep neural nets are so powerful, and we have never been able to realize that, right? In the past 30 years. So okay, so today we're going to first talk about what is deep neural networks, right? And also how to perform prediction with neural nets. And we still have some time. We're going to talk about the training framework. And then on Thursday, we'll focus on a key technique in training neural networks, which is called backpropagation. So everybody will be asked to implement your own backpropagation algorithm to train a neural network. So, so before we proceed to the details, right? So we need to first look at, okay, where are we, right? What kind of how can we organize what we have learned so far, right? Where should we find a place to put our deep learning topic, right? So far we have seen quite a few learning algorithms, right? Decision trees, either boost, bagging, least mean square, and so on, right? And through learning those algorithm steps, we also learned quite a few general learning principles, right? The concept of overfitting, principle of mystic bound driven. I'm talking about perception, right? And pack learning, what is hypothesis space, what is VC dimension, and how VC dimension relates to the complexity of hypothesis space, and so on, right? And also what is regularized empirical risk, right? Minimization, right? So in the past few lectures, we mainly focused on the learning for linear classifiers. So obviously, linear classifiers choose a quite simple hypothesis space or hypothesis class, right? Because all the candidates in your hypothesis space are just linear functions, which obviously are not powerful enough to cover complex practical problems, right? So how do we address that problem, right? So we talk about the kernel trick. Right? So kernel trick is a kind of a neat, smart idea, which we can directly extend our linear classifiers to nonlinear classifiers without changing the algorithm details, right? Especially the obvious case, right? The most successful case will be the combination of kernel trick and support vector machines, right? That's why we introduce like dual form of support vector machines, and also from which we can plug in our kernel, right? So this is one way to enhance our learning, right? Learning models, learning algorithm, right? Obvious, but this is kind of like indirect, right? So I want to build up a nonlinear classifier. What should I do? I first construct a linear classifier, and then I plug in some smart trick like kernel trick, and then I extend linear classifier to nonlinear classifier. Right? Why not we just build up a nonlinear classifier from scratch, right? Without some intermediate steps. So the answer is obvious, yes, right? So artificial neural nets is one typical example, right? So it actually is most dominant nonlinear classifiers. So here's the outline, right? So we're gonna first talk about what is neural network. Basically, what's the hypothesis space of the neural networks? We'll talk about what kind of functions are the neural network can approximate. What's the structure? What kind of structures determine a specific neural network? You see that neural network is really powerful. It's really expressive. It can almost approximate arbitrary function. And then we'll talk about how to predict with a given neural network. Why? Because this is important. Even you are doing training, right? Every time you actually use the current set of neural network parameters to make predictions, and then compare against the ground truth, and then adjust your weights accordingly, right? This is a training procedure. That's why we're gonna first discuss about the prediction step, and then we'll talk about the training framework, and then we'll talk about the K computational step in the training, which is about derivatives, and which is about the backpropagation. And finally, we'll talk about when you apply neural network in the practical applications, what is the practical concerns, what is the suggestion. Okay. Any questions so far? Great. So to give a formal definition of artificial neural net, let us look at some concrete example which we have seen before, right? So this is a graphical representation for a linear classifier. Sometimes we refer it also to linear threshold unit because it comes from the neural network literature, the early literature, right? So when we represent the prediction function, of using linear classifier, we can use this graph, right? So we use several nodes to represent the features or inputs from data, right? So suppose we have 4 features from x1 to x4, and also we introduce a constant feature 1. Right? Then we're gonna collect all those features into an intermediate node, right? And so we draw an edge, right? An edge which connects the incoming node and this intermediate node, and associated with each edge is a weight, right? So W1 for X1, W2 for X2, W4 for X4, and also for the constant feature, the associated weight is actually the box, right? And then when we pass this input value through this weighted edge, it just means I'm going to amplify the incoming signal by the weight. So actually, the signal arrives here will become W1 X1, right? Similar, this input, when it was sent to here, it will become W2 X2, right? W3 X3, W4 X4, and 1 times B, so you got B, right? So now you got 1, 2, 3, 4, 5 values coming into this node, right? And then we can see that there is an operation here, sigma. Sigma means summation, right? So that basically means, okay, I'm gonna sum over this incoming values as my outcome, right? So this intermediate node, we call it performing a dot product operation. Why? Because if you will, as a vector-vector representation, right? If you will, all the input nodes as one vector, this is a feature vector, right? Augmented feature vector with this constant feature 1. And then if you will, all the weights on the associated edges, including spots parameter B, it becomes another vector, right? Weight vector. So the summation operation is equivalent to the inner product or the dot product between the input vector and the weight vector, right? That's why it's called dot product operation, right? So, and then the next step is that this intermediate node will further send its value to a second node, right? So this node receive the incoming value and then perform a threshold function and get the final output. Okay, so through these operations, we're essentially performing a classification using a linear classifier, right? So the dot product essentially perform this, right? W transpose X plus B, right? But if we use the augmented representation, right? Fold 1 into W and fold 1 into X and fold B into W. It is the pure dot product operation, right? And then you take sign from it is actually sending this dot product result to this threshold unit and then to the threshold, right, sign. So you can see that we can use a simple graph, right, to represent this series of operations to perform classification, right? And then the learning essentially is to identify the parameters W and B, which are associated with those edges, right? So of course we have a variety of algorithms like perceptron, SVM, and so on, right? And the learning is essentially to minimize some loss defined on the training data, right? And to optimize WB. So any questions so far? This is just to review what we have mentioned before. So now, what if we want to extend this simple model to a more complex nonlinear model, right? So if you would like to build up some Lego or something like that, you know that the basic units or basic items in these Lego toys are really simple, right? But if you can smartly combine them together, you can build out whatever complex shapes, structures, right? So the construction of neural nets is kind of similar to building your Lego things, right? So instead of using just one graph like that, right? why not we just combine multiple linear threshold units to build up or to construct more complex classifiers? That's the idea, right? But then how can we connect or how can we combine different linear threshold units? We can look at inputs, right? So the inputs x1, x4, and 1 in the original linear threshold units are assumed to come from the training data, right? They are here, right? They come from data, right? So now why not we just assume they are not come from data? They might come from the output from other linear threshold units. In this way, we're gonna connect the outputs from previous linear threshold units to the current linear threshold units, right? And we just concatenate them together. We can build up more complex models, right? So to take a specific look, right? So this is the naive linear threshold unit, right? So now I want to use that as a basic unit or basic break to construct my more complex classifier. How can we do that? Okay, I no longer assume the input to this linear threshold unit directly comes from data. Instead, it comes from other linear threshold units outputs, right? Suppose this is the original features from data x1 to x4, right? So I'm gonna first feed them into a linear threshold unit, then to get output. And this output will serve as the first input to our target linear threshold unit. Right? And how can we get the second input for our target linear threshold unit? We can just construct another linear threshold unit on top of our original inputs, right? So get second linear threshold units. Of course, they're gonna use different weights and bias, right? You get, and after some mapping, right, you actually got the output, and this output will be the second input of our target linear threshold unit, right? We can continue doing this and to construct another two linear threshold units to get another two inputs for this target, right? So in this way, we have constructed a two-layer feed-forward neural network. So the intermediate layer, which comes from the outputs from the linear threshold units in the previous layer, is called the hidden layer. Why it's called hidden layer? Because it is not directly from the data. It actually computes from some intermediate steps. And we call the final prediction calculated from the linear threshold units closest to the output as output layer. So basically, that means, okay, the output of this particular linear threshold unit will serve as our final output, so-called output layer. And the input layer, which directly comes from data, is called input layer. And then we can view the hidden layers, right? The nodes, the values, the hidden layer can be viewed as kind of like transformation or representation from the original data, right? So you throw some linear threshold units, and later we'll say we can use other types of units to construct this hidden layers, right? So they actually gave some kind of good representation of the data, and then feed this new representation into our target or output layer to compute the final prediction. So, before we proceed, right? Any question regarding the whole construction? So it looks really easy and intuitive, right? Yeah, that is how we build up neural networks. Use very simple rule, use very simple model as some kind of break, and you just stack them together, extend them widely, extend deeply. You will finally end up with very complex models. No question? Great. So now, usually, I mean, for simplicity, people won't like put two explicit nodes here, right? Instead, we're gonna merge the two nodes together into one node. This node, this merged node is called a neuron. So you can see to compute the value of a neuron, you're gonna first do some dot product, then apply some threshold function. But here is threshold function. But actually, in general, you just apply some nonlinear transformation, and then this value is called neuron. So if we count how many neurons in our simple two-layer feed-forward neural network, 1, 2, 3, 4, 5, right? And 4 in hidden and 1 output. Right? So we can, if we are not satisfied the expressiveness of these two hidden neural nets, right, we can continue to add more layers, right? So the trick is the same. The rule to add more layers is the same, right? We can just replace the input layer here by the output of another set of linear threshold units as the hidden layer, right? So you're gonna have two hidden layers, and then your original inputs at x1 to x4 will be served as input from some another set of linear threshold units at the beginning. So actually, you can construct arbitrary deep and arbitrary wide neural networks. So after saying this concrete example, let us try to formalize the definition of artificial neural net. Right? So first, to summarize, right, neural networks in general are a robust approach to approximate real value, discrete value, or vector value functions. Actually, you can approximate arbitrary functions. And they are among the most effective general purpose supervised learning methods currently known, especially when you deal with complex and hard to interpret data like real world sensor data, like image data, right? And neural networks usually perform extremely well. And the key techniques to the neural network is called backpropagation algorithm, and we'll talk about later. And this is essentially application of the chain rule. Otherwise, if you don't use backpropagation to compute the derivative of the parameters in neural networks, it will be very, very inefficient. So artificial neural nets are enlightened from the biological neurons, right? So here, just to give a very superficial introduction of biological neurons, because I'm not an expert on that. But neurons are kind of like very common in animals, including human beings, brain system, right? So a lot of biological research reflect that neurons are kind of like a basic component in your neural system, right? So it basically contains like dendrites and also axons which generate and send the signals. However, the resemblance between artificial neural networks and the real neural networks are just here. We have some nodes we call neurons, and then we have some message passing mechanism, which is kind of a counterpart to axon. But that's it. But how the messages are generated and how they are passed are totally different between the two types of system. So we can at most say modern artificial neurons are inspired by biological neurons, but you should never say, okay, modern neural networks are kind of like simulating or similar to biological neurons. If you conclude that, like you're gonna piss off the real computational, biologists, biological neural experts, because many fundamental things, the two types of like so-called neural system are totally different. Okay, so in artificial neural network, how do we construct neurons? Right? How do we calculate the value associated with neurons? So every neuron is going to accept a collection of inputs, which for convenience, we're going to use a vector x to denote that. Right? And the output of this neuron is calculated by two steps. The first step is to apply a dot product with some weight vector and plus a bias parameter b. So it's essentially to calculate some linear function to x, w transpose xb. In some literature, they say this is a kind of affine function to x, but doesn't matter. They are the same. And then we need to apply some transformation over this linear function value. So this transformation is referred to as activation. And this activation is usually chosen to be nonlinear. Like if you look at back our linear threshold units, right? So these two steps actually compute a neuron, right? As we mentioned, we just summarized, we merge them together into one node, we call it neuron, right? So the dot product node computes W transpose X plus B, right? And then the threshold node actually performs this activation. And the threshold function itself is a nonlinear transformation, right? But someone asked, right, do we have other activations? The answer is yes. We have a lot of activation functions. And like the simplest one will be linear unit, meaning that the activation of Z is Z itself. So it's actually do not perform any transformation, right? And this is a threshold unit, which is take the sign, right? And by the most commonly used are the following three. You take sigmoid, the sigmoid function of Z, right? Of this linear function, right? And rectify linear. It takes max value between 0 and Z. It's kind of like similar to hinge-offs, right? And you take tanh function. But in addition to the three, you have many more activation functions. This like sinusoid, sine, Gaussian polynomial, etc. You have a lot of like, but these three are kind of like most popular and most successful ones. Any questions so far? Everyone is comfortable? Everyone is happy? Okay, yeah, let us continue, right? So given the definition, formal definition, how to construct neurons, right? The basic unit, or you can view it as basic brick, right? You construct a neural network, right? What is neural network itself, right? So formally, you can view neural network as a function that converts some inputs to the outputs, and this function is represented by some directed acyclic graph. So basically, you can view it as a graph, right? And you connect all those neurons together, and this graph is now allowed to have cycles. So nodes are organized in layers, right? Layer by layer. And those nodes correspond to neurons. And edges connect different nodes across layers, and edges are associated with weights. Here's one example, right? So the bottom layer is the input layer, and the middle layer are the hidden neurons. In output layer, but here we talk about two outputs, right? Is the output layer, right? So between those nodes are edges connecting them together, right? I just ignore the arrows, but they just saying the arrows are always from up to bottom to up, right? So it's actually like that, right? So associated with each edge will be one weight, right? So all the parameters that determine the neural network are the weights on those edges. So the training is essentially to estimate the edge weights. So how can we define a neural network? Essentially, we need to define the structure of this graph. Right? How many nodes, how many layers we're going to choose, right? And how many nodes per layer, and how the nodes are connecting with each other, right? The nodes are usually connected across layers rather than connect them in the same layer. And then what is the activation function on each node, right? To get the value of each node, namely to get value of each neuron, how do we apply the activation function, right? And once we have figured out this, we have finished our modeling of a particular artificial neural network, and the remaining thing is to estimate the weights on those edges. So the definition of a neural network is also referred to as the architecture of the network. So typically, it is fixed before the learning procedure. So we usually assume, okay, the neural network is predefined. Its architecture there, the choice of activation is there, and the learning procedure is to estimate the edge weights. Any questions so far? Great. So so here I give a very brief history of neural nets. So it's a long history research topic. So it can be traced back to 1940s, right? 1940s. These two pioneer researchers, they showed linear threshold units can compute logic functions. So you can see that linear threshold units, right, come from here. And or in other words, you can view linear classifier as a special case of a neural network, right? And then in 1949, Hebb suggested a learning rule in linear threshold units. This learning rule is essentially a perception rule. Right? And then in 1950s, this is about perception. Right? So that's what we discussed before, right? And then in 1969, Minsky and Papert studied the neuron from geometric perspective. And in 1980s, there are some other type of neural networks proposed. It's called convolutional neural nets from some Japanese scientist, and Yalan Kun, who's a recipient of a Turing Award, I believe last year or the year before last year. I forgot, right? And then backpropagation algorithm, right? All those key techniques were developed in 1980s. And then from 2003 to today, you see more computational advantages, more data, more deeper networks, but are enabled because of the powerful computational platform. So here we have finished the definition, introduction of the definition for neural networks, right? And this essentially talk about what is hypothesis space of neural networks, right? The next thing is about, okay, what functions do neural networks express, right? So how powerful your hypothesis, your neural hypothesis space is, right? So to give a concrete example, right? So we start with a single neuron with threshold activation function, which is essentially a linear threshold unit, right? We know that they can only classify linear, they can only linearly classify data points, right? Because they correspond to lines or hyperplanes. Right? However, if we just use linear threshold units to build up two-layer artificial neural network, it can represent any general convex polygons. If you further extend to 3 layers, it can approximate or it can represent any union of several convex polygons, right? You can see that 1, 2, 3, 4, right? You have 4 polygons here. So there is one famous theory called universal approximation theory, which can tell us how powerful neural networks are, right? So any continuous function can be approximated to arbitrary accuracy using just one hidden layer of sigmoid units. So basically, if you just construct a one-layer neural network, you use sigmoid as your activation function, as long as your number of neurons are enough large, meaning that your neural network is enough wide, you can well approximate any continuous function to an arbitrary degree of accuracy. And in the further development of this theorem tells us that the approximation error is actually insensitive to the choice of activation functions. You use 10H, you get similar results. But people find that this is about something new in the deep learning, right? People find that although you have enough wide neural network which are powerful to approximate arbitrary function, but the learning itself is much more difficult. It requires a lot of training examples. Right? That's why right now people tends to use kind of like not that wide neural network, but you kind of add more and more layers. And empirically, people find that you can use much less samples to achieve the same kind of accuracy to an arbitrary continuous function. Rather than for just single layer, you have to make your neural network to be extremely wide, right? And then the training is very hard. And two-layer threshold networks can express any Bloom function. Right? So now I want to ask a question: Did we discuss any model which is also flexible to express any Bloom function? Any idea? Have we discussed any model before which is also expressive enough to express any Bloom function?
No.
No?
So we have discussed, we have only discussed linear models up till now, and the only one that is non-linear is SVM. So the other linear models, I don't think they'll fit. Maybe decision trees.
Yes, exactly, right?
Yeah.
Don't forget our very first model, right? Our very first model is not a linear model, it's a non-linear model.
Yeah. So decision trees can.
Decision trees are also flexible enough or expressive enough to represent arbitrary Bloom function, right?
Right.
Now you can see that we only use two-layer network by just using this simple threshold network, the threshold function as the activation. We have like same kind of like expressiveness as decision trees. We'll add more layers to be even much more expressive than decision trees. So here's just a few results, right? We actually briefly covered when we talk about this dimension. Right? When we the VC dimension of a threshold network with the edges E can be represented this way. With big O size of E comes logarithm size of E. And the VC dimension of sigmoid networks with no V and the edges E are given like here. So you can see that the more the nodes you have, the more the edges you have, the larger the VC dimension you have. Like, so this is actually a lower bound, upper bound. It's not the actual value. Like, so so you can see the larger the network, actually the more expressive your network. Why? Because the larger the VC dimension is. Okay, any questions so far? Okay, so yeah, those are about preliminary definition about neural networks. Someone asked, okay, in addition to the feed-forward network we have mentioned, right? You just construct those neural network layer by layer, and each neuron is computed from inputs from the previous layer, and then from linear combination and nonlinear activation, right? In addition to that, what else neural network do we have, right? Another very popular and important neural network is called convolutional neural network. Uh, is most often used in dealing with images. Uh, but actually, convolutional neural net is even simpler than the feed-forward network. So we're not gonna cover them in this class. But as the and once we have gone through all those topics, the convolutional neural nets is really easy to know, right? It's easier to learn, right? Because the computation, all kinds of stuff, so actually the same. So I'll leave one exercise for you guys, right? And show that if we have only linear units, meaning that you do not perform any nonlinear activation, your activation is just linear activation, then no matter how many layers you put in constructing your neural network, it doesn't change the expressiveness. In other words, it is the same. It has the same expressiveness as just linear functions. So perhaps it will appear in your final homework. Okay. So now let us proceed to the next topic. Wait a second. That is about the forward pass. Can everybody see the slides?
Yeah.
And also the transition is okay, right?
It is.
Okay, great. So we haven't finished the introduction about the definition of neural network and how expressive it is, right? So next we're going to talk about suppose you're given a neural network, you know all the parameters, namely those weights on the edges, right? How can we give a prediction? Why should we first talk about that? This is important, right? Because when you train a neural network, you essentially always use the current net parameters to make a prediction, and then compare against the ground truth, then adjust the weights accordingly. Like, so you need to first know the prediction rule of neural network. Right? So here is one example of network. We're gonna based upon that to explain the prediction rule. Right? Let me use this one. Okay. So this is a simple two-layer neural network, and we're gonna use some like naming convention. Why? Because there are many nodes in this neural network representation. Right? We do not be confused. We do not want to be confused. Right? So so we can see that those graded circle or node, they just represent bus feature or constant feature. You can view them as one. And for the other nodes, there are actually the neurons, right? We assume in our example, we're going to use sigma activation function. So basically, the computation of this neuron, like Z1 and Z2, is going to first linearly combine the inputs from the previous layer, right? The dot product. And then you perform sigma function over the dot product result, you get the value of those neurons, namely Z1 and Z2. And once we got all the neurons in the second last layer, right? The last layer will be output layer, right? When we calculate the value of the output layer, namely y here, we will not perform nonlinear activation function. Instead, we just use linear activation. In other words, the output y is simply a dot product operation or a linear combination of the inputs from the previous layer. And then you get y. We do not perform any nonlinear activation function. Someone may ask why, right? There's no reason. It's just a convention. So in this area, like people do final prediction, like in the last layer, the final prediction is simply a linear combination of the inputs from the second last layer. People usually won't add one more nonlinear activation on that. But you might ask, like, why not? Like, there's no reason why not. You can, if you feel like pissed off, right? If you're not comfortable with that, you can do that. Definitely, it's definitely allowable, right? But I'm just telling you the convention, the tradition, people just doing like that. And doing this has another benefit in some theoretical analysis, because you can view the final output as a linear combination of some output in the second last layer, right? Z0, Z1, Z2, right? Z0, Z1, Z2 can be viewed as nonlinear functions of the original inputs. So you essentially have a linear combination of several nonlinear bases. So you have a bunch of algorithm theorems which will come up. Okay, any questions so far? Okay, so and then to differentiate different edge weights, right? We're gonna use this convention. So we use the superscript to denote the target layer the edge connects to. Like for the edge connects between 0, x0, and z1, right? The target layer is a hidden layer, so the superscript here is h, right? And for the edge here, right, it connects z1 to the output node y, right? So because target node is the output layer, we use O, like in the superscript. In the subscript, it just use a pair of indices, like from to, like from is the index of the source node where the edge comes from, like the edge starts on, and the 2 is the index of the destiny node, right, where the edge comes to, right? So if we take a look, this edge connects the node Z0 in the hidden layer and the node Y in the output layer, right? So the target layer is output layer, so the superscript is O, right? The subscript is the pair of the source node index and target node index to 0. And 1 here it just means, okay, we use neuron 1, we index the output node from 1. So we can use another example like this one, right? So this edge connects x2 in the input layer and z2 in the hidden layer. So the target layer is the hidden layer. So we in the subscript, in the superscript, we use h, right? And in the subscript, the from node is indexed by 2, right? The to node indexed by 2 as well. So we finally denote this edge weight by W2 to H. Okay. So now, given those weights, right, as we mentioned, right, the whole neural network are only determined by the weights associated with each edge, right? So given an input x, how can we compute output? We just do it layer by layer. So start with the bottom layer, which is the input layer, and then compute each neuron in one layer above. Once we get all the neurons in the one layer above, we use them as input to compute all the unknown neurons in one layer above. We'll do it layer by layer until we reach the top layer, from which we can compute the output value. That's why it is called a forward pass. We start from input layer and to calculate all the neurons layer by layer until we reach the output layer. We move this is the forward direction. This is called forward pass. To be more specific, right? So we start with the input layer, x0, x1, x2, right? We're gonna first compute the neuron Z1 in the hidden layer, which is one layer above, right? So how do you compute Z1? We just do first perform a linear combination of the incoming nodes connected to Z1, right? And then perform one activation, nonlinear activation over the linear combination to get Z1, right? So we see that x0, x1, x2 all connect to Z1, and x0, which is the constant feature 1, right? So it multiplies with the associated edge weight W01H. That's where this W01H comes from, right? And for X1, right, multiply the edge weight, the weight of edge connecting X1 and Z1, right? The weight will be denoted by W11H, target node. Target layer is H, and the source node and target node 11, right? Times X1, and also X2 multiplying with the weight of the edge connecting between X2 and Z1, right? So this weight will be denoted by W21H. Why? The target layer is H, is superscript, right? But in a subscript from node indexed by 2, right? 2 node indexed by 1, right? W21H times X2. And you get this linear combination, this dot product, and then you apply sigma activation function, you get Z1. Right? Any question? Everyone's good, right? It's pretty straightforward. Right? And similarly, we'll compute Z2, right? And Z2 is computed in the same way. We have all the three nodes in the previous layer connecting to Z2, right? So first compute the dot product X0, X1, X2, and with the associated weight edges, right? W0, W02H, right? So because something we should be aware, right? Because each edge is different. So the associated weight will be different as well. That's why on the edge between X0 and Z2, the weight is denoted by W02H. So it is different from W01H, which connects X0 and Z1. So this is connects X0 and Z2. So I have a different X0. Right? And plus W12H on the edge, which connects the X1 and Z2, right? And W22H here connects X2 and Z2. So now we get Z1 and Z2, right? So because Z0 is constant feature 1, right? So now, so far we have already known all the hidden units, all the neuron values in the hidden layer, right? And what's the next step? We're gonna use them as input to compute all the neurons another layer above, right? Which will reach the output layer, right? So now we can compute the output neuron Y by using Z0, Z1, Z2 as the input, and then we perform linear combination of them, like the dot product, multiply X W0 10, W110. Why is W110? The target node is the target layer is output layer, right? And source node, that's node, right? And the source node, that's node, right? And remember, when we calculate the neuron in the output layer, we do not perform nonlinear activation function. We only leave the linear combination. So in this way, we have computed the output neurons value, which will be served as the prediction. So any questions so far? Everyone's good? No question? Okay, great. So now let us proceed to, let's proceed to the training step. Can everybody see the slides?
Yeah.
Yes.
Okay. And how about transition? It's okay, right?
Looks good.
Okay, nice. So far we have given the definition of neural nets, right? We also talk about the prediction rule, right, which is really straightforward, right? So, and now we can talk about how to train a neural network. So, what is the training framework? How can we efficiently update the weights of the neural network during the training procedure, right? This will be based upon this key technique, which is called propagation, and we'll see later. This is essentially an application of the chain rule. So it's a smart use of the chain rule based upon the neural network architecture. So we can highly efficiently compute the gradient with respect to each weight on the edges. So before we go to the detail, right? So first thing to talk about the whole framework to train a neural network. So suppose we have defined our neural network, meaning that we have designed this network architecture, how many layers do we have in total, and how many nodes per layer, and how the nodes between different layers are connected to each other, and what is the choice of activation function. You're using sine function, or use ReLU, or use 10H, or sigma. Okay? And then we have also collected a bunch of labeled training examples, which can be viewed as pairs of input and output. So input feature vector and output label Y. This is our setting. And our goal is to estimate the weights of the neural network based upon those data set. Right? So those weights are all on those edges, right? So how can we do that? A first observation is that for any given neural network, meaning that we have a fixed architecture, you have a choice of activation function. Right? We will calculate prediction from the forward pass. The prediction value is essentially some function determined by both the input feature vector and all the weights of the neural network, right? So now, if you want to estimate the weights, right, what kind of training protocol can you think of? Any thoughts?
Can you repeat that?
Yeah, I mean, can you develop a training procedure for neural networks? So we have discussed, right, the output of neural network can be viewed as a function of your input and also weight, right? So given this observation, right, can you come out some strategy to train a neural network, or in other words, to estimate those weights?
Gradient descent? We can use gradient descent.
Yeah, of course, gradient descent, but under which we can use gradient descent, right? The whole procedure. What is the whole procedure of performing gradient descent?
I guess, would you use gradient descent on each individual weight that's independent of each other? But I guess I don't know how much farther than that you would do.
Yeah, of course. I mean, this is about detailed strategy, right? But before the gradient descent, we need to get clear what is our objective function, right? So what kind of objective function can you use for gradient descent?
Convex?
Oh, I mean, it's not necessarily convex.
Okay.
Think about it like to be even simpler, right? It's not It's not that it's not complex. It's just very simple.
Like, would you just go for like small, I guess, achievements, just like small goals that when all the weights are put together, you get that bigger goal?
Yeah, of course. Yeah. Could it be more a little bit more specific?
Can you take a similar approach to support vector machine to SVM and like kind of minimize a function similar to that?
Yes, exactly right. Just like that. It's actually, I mean, the framework is the same as the previous models we have learned. We're trying to come out some objective function based upon the training data, right? And then our task is to minimize this objective function or optimize this objective function to find the best weights of the neural network, right? So this objective function is really referred to as a loss function, right? So remember, in general, when we define a loss function, it's just to compare against the prediction made by your model and the ground truth, right? And the loss will assign some cost to penalize two wrong predictions, right? So the better you make predictions, the smaller cost you're going to pay for that. A similar idea or similar strategy can be applied in learning neural networks. We're going to define some loss function on the training data. And the loss function, of course, will be applied over each individual examples, as you guys have pointed out, right? Lead to increments, lead to improvement, and additionally, right? And accumulate to the whole training set, right? And the loss over each training example will be a loss between the prediction made by a neural network. Remember, it is a function of the input xi and also the weights, right? And the ground truth value yi, right? This log function reflects how your neural network predictions fit the training data, right? And perhaps we need to add some regularizer, just like SVM, right? So we can add some square norm over the weights, but just be clear, you add the same kind of same form to regularizer as SVM. Does not mean you encourage large margin, right? Because for neural networks, it doesn't have a concept about the margin, right? So far we have seen this strategy worked for quite a few learning algorithms like support vector machines, right? We have come out some objective function, which is the regularizer plus the hinge loss over the training data, right? Perception, although it is kind of mistake driven, right? But at the end of the discussion of the support vector machines, we have derived that perception essentially is to optimize some loss function as well, right? And this means for regression. And each learning algorithm essentially choose to minimize a different loss function. So all those are linear models, right? Of course, same idea applies to nonlinear models as well. So now I want to ask, what kind of loss function can we use?
Like mean squared error.
Yes, exactly right. It's the same as the least mean square regression, right? Why not just use L as square, right? Square difference between your neural network prediction and the ground truth output, right? And take square, right? So now to take a close look, suppose we have given the values of those weights, right? And then we can use forward pass to calculate the output value for any input x, right? So, and suppose the true label for this number is y, right? And then we can make a square loss in this way, right? We just calculate the difference between the neural network prediction and the ground truth prediction, right? Then take square, and you multiply a factor half, right? Why we should use half here? We just need to we just want to cancel the coefficient. We will take derivative. If you take derivative, you have a 2 factor of 2 in front of this parenthesis, and now you multiply 1/2 to cancel out. And someone asked, do we have others laws? Yes, of course. But square laws is one type of most commonly used loss functions, even applied to neural networks. So now we haven't come out. Suppose we haven't come out the training loss over the training data, right? Plus we have added some regularizer, right? So now the remaining question is reduced to an optimization problem. Right? How do we solve this optimization problem? Any thought? An idea?
We just use the loss function we just talked about. Couldn't we just use gradient descent?
Yeah, gradient descent is one way, right? But how do we deal with large data, right? We will mention that the power of the deep neural nets mainly embodied in large data, right? So we can really assume you have like millions or even billions of training examples. If you use gradient descent, of course it's doable, but it will be very, very expensive.
So you mean we should probably then use like stochastic gradient descent?
Yes.
Okay.
Yeah, we're gonna use the framework we have used before, right? Stochastic gradient descent. Honestly, there are some works, some methods which can use gradient descent or deterministic optimization approaches to learn the weights. That's doable for some scenarios, for some applications. I do agree, but the kind of like a standard training approach for neural networks is stochastic gradient descent. Okay, so that is just a review of the whole framework for stochastic gradient descent, right? We have used it to use it for quite a few learning algorithms. Right? So same framework applies to neural networks. Suppose we're given a training set, right? Xi, yi, I from 1 to big N, right? So this is our loss function for neural networks, right? So we're gonna first initialize the parameters of the neural network, namely all the edge weights. Then we're gonna pass the data set multiple epochs, right? So we need to pre-specify the number of epochs, a big T. Right? And then inside each epoch, we first randomly shuffle the training data, and then we'll look at each training example, right? Xi, yi, and then treat this example as the entire data set, just to duplicate them, right? Suppose you have a big N number of training examples, you just duplicate this single example for big N times, right? And then you fake another entire data set, then you compute the gradient of the loss on this data set. Because this data set only has one distinct example, so you only need to compute the loss over this single example, then you multiply it by the size of the training data, right? And then this gradient is called stochastic gradient. We have mentioned before, this is essentially an unbiased estimate of the true gradient, right? And then we're going to use the stochastic gradient to update the neural network weights, and we'll multiply a step size gamma t, right? And subtract W by this step size multiplied stochastic gradient. We get one update of the neural network weights. Right? Again, to ensure the convergence of your stochastic gradient descent, you have many tricks or gamma t, right? You need to ensure that the summation of gamma t is diverged, but the square summation of gamma t is converged, right? And then you finish one update, you look at the next training example, You do the same thing. You compute the stochastic gradient descent and update again. You do it again and again until you finish one epoch, and you move to the next epoch, and until you finish all the epochs, you're going to finish the weights. So any question regarding this whole framework? I think I believe everybody is familiar with that. Okay. So one thing I want to emphasize, usually the loss function for the neural network is non-convex, meaning that it might have many local minimums. So if you write down the landscape of the neural network objective, it will be like that. So it's not like square laws for the linear regression model, which is convex function. It only has one global minimum. For neural networks, you often have many local minimums. So stochastic gradient descent can only guarantee to convert to one local optimum. It does not guarantee to convert to some global optimum, like the smallest local minimums. It does not guarantee. In other words, the initialization of this weight vector, of those neural network weights, really matters. If you are near some local minimum, which is good, and then it is very likely you converge to this good local minimum. Right? This is not good local minimum. Actually, this is some good local minimum, right? If your initialization is at here, right? So it's likely that you're gonna converge here, right? And converge here, you're gonna have a better objective function value. Then you converge here and converge here, right? So that's some kind of like common observations in neural networks learning. So if you change initialization, the performance might change dramatically. And you'll see that, I mean, in the modern neural network libraries like TensorFlow, like PyTorch, they have integrated many initialization strategies. And people have found that if you just follow that strategies to generate the initial parameters for W, they usually converge to some local minimum, which give you good performance. So now we have to talk about the detailed framework to learn a neural network. That is the stochastic gradient descent. There's nothing different from the framework we mentioned before, right? We just need to pay attention to the non-convexity of the neural network objective function. Oh, by the way, I want to ask why this objective is not convex. Usually, why is this objective usually not convex? Any thought? Any idea?
Does it have to do with expressing things as a union of convex polygons? So like a local minimum would maybe correspond to some kind of minimum for like one part of the union.
Oh yeah, that's one way to think of that, right? But here, I just want everybody to think about how you compute this, right? So the computation of this procedure is non-convex, nonlinear to W, right? Why? Because every time you start from some input, you do some linear combination with W of W, and then you perform some nonlinear activation function, you get the units, right? You get a hidden neuron, and this hidden neuron linearly combined together, and then apply some nonlinear activation function, you get one neuron one layer above, right? You do it again, you can will them. It is kind of like nested, a series of nested linear and nonlinear operations. So finally, the output is often highly nonlinear, non-convex to W. Right? And now you put this output into some objective function. Of course, that objective function will become nonlinear and non-convex as well. And it doesn't like, it is not like a least mean square objective for linear regression, right? Because the prediction function of linear regression is simply a linear function of input and W, right? So then you put them in a square loss function, you still end up with being complex, being convex, right? But for neural networks, because the computation, the forward path to compute the prediction itself is very complex. So it's not, usually it's not convex at all. Okay. So do we solve everything? The answer is no. Right? We haven't talked about how to compute this, right? How to compute the gradient of the loss with respect to the neural network parameters. So if the neural network is a differentiable function, right? So we can find the gradient in principle, right? And like if you use tanh, sorry, I don't need to. Or sigmoid, those are this is a continuous nonlinear activation function. Of course, you can in principle you can apply you can just calculate derivative, right? But what if the activation function is not differentiable, like ReLU, right? ReLU is actually max function, max between 0 and your input, right? And then you're going to use a subgradient, right? Or sine function. So this is determined by the activation function, loss function. But from a aspect of a calculating perspective, that won't be a big problem. Right? And for least mean square regression or support vector machines, you can view them as a special case of neural network, which you only have one layer. It is pretty easy to compute. Right? However, if you have many layers for neural network, the computation will be much harder, right? Because you're going to compute the output with respect to many weights across all the layers, right? And the number of the weights associated with those layers can be tens of thousands or even millions or even billions. If you take a look at the Google Brain, right, they are addicted to train a huge neural network, like with millions or even billions of neurons. Right? So if you calculate the gradient with respect to each weight independently or separately, it will be extremely expensive. Right? So we do need some smart trick to avoid redundant computation and to efficiently calculate the gradient for every weight, so that we do not waste our computational power. So what kind of method to compute those gradients efficiently, right, without any waste? It is backpropagation. So we're going to discuss about backpropagation in detail on Thursday. And thanks for joining the lecture today.